Okay, so this is my final presentation for basic probability theory. I'm doing page 114, number 8, and we're going to use the Poisson distribution to find the expectation of r times r minus 1, r minus 2, all the way to r minus r plus 1. And we want to prove that this is equal to lambda raised to the r, given the probability of ER that the variance is lambda raised to the r. So to begin, I'm first going to start with the expected value of a Poisson problem. So what we have to know is that if a random variable x is Poisson, we have the probability of x equals k is equal to lambda k e raised to the lambda over k factorial 4 when k is a positive number, 0, 1, 2, and so on. So anytime that an event is a non-negative integer, we can use this particular equation that was given to us in our book, and we want to complete this expectation by using what we know about the expected value, which is the sum of an expected value. And the sum of this value and the probability of it says that we have k times lambda k e to the negative lambda all over k factorial. As we've seen in the binomial distribution, we can manipulate this so that we get the sum of two probabilities for a new distribution. To do that, we are going to start by changing k equals 0 to k equals 1. And to cancel out the k here we have in front, we're going to bring a k in front of our k factorial, so we'll be left with k minus 1 factorial. And we're going to bring a lambda out, so that we'll have lambda k to the minus 1 and e to lambda. This will result in our k's canceling out, so that we will be left with a lambda. We can bring the lambda out front. Summation of k equals 1 in infinity is lambda k minus 1 e raised to the negative lambda all over k minus 1 factorial. What we are going to do, sorry, I didn't mean to go that far down, now is we are going to plug in or kind of substitute a new value for k minus 1. So we're going to say that k minus 1 is equal to j. The purpose of this is so that we can continue kind of moving things around and canceling out. So we will get lambda, the sum of infinity, and we're going to start with j equals 0, where we'll be left with lambda to the j e to the minus lambda all over m j factorial. Sorry, I kind of got lost in my notes. So now what we're going to do is pull out e to the minus lambda. So we're going to have e to the minus lambda, the sum of infinity j equals 0 is going to be equal to lambda j over j factorial. And what we find is that this is actually an exponential. It's going to give us e to the lambda which gives us that the expectation of this particular random variable is just lambda, our parameter. So we're going to use this same idea to complete the problem. And we are going to take, this is the actual problem now, so page 114, number 8. We are going to take the summation of k to 0, and we're going to have k times k minus 1 based off of what we were given, and this is going to proceed all the way to k minus r plus 1 over k factorial e to the negative lambda and lambda to the k. We can continue to manipulate this like we've done before, which will give us the lambda out front. So we're going to have lambda r, the summation of k to r. So instead of the k to 0, yet again, we're going to change it so that we can have a better point of view of what's going on. And we're going to have 1 over k minus r factorial with e to the negative lambda still, and lambda is now to the k minus r. Continuing manipulating this, we are going to end up with the lambda of r e to the negative lambda e of x, which results back to lambda r. Therefore, the expectation of r minus 1, r minus 2, all the way to r minus r plus 1 is going to have the variance of lambda to the r.